what you have to do.
Yeah, but it's already, I mean, I can get that from the website. Yeah.
I don't know how much value there is
Yeah.
up there on the web anyway.
Yeah.
Eventually, yeah.
I don't know, before you do anything.
Yeah. No, yeah.
Is someone going to introduce me?
Yeah, I mean, I'm just going to say, you know, the very basics.
Okay, that's great.
No poetry, trade. Just want to wait till this is it.
Say again?
Just want to wait for this to get here. I think she would want to see everything.
Just the AC. It seems kind of hot. So sorry. I've had that reaction.
Sorry, yeah.
Okay.
I think there's a problem with it. It's not. Okay, I guess we'll start. Okay, so our speaker today is James Cummings, who's professor of mathematics at Carnegie Mellon. James started his PhD at Cambridge before coming to the States to work with Hugh Witten. He's now one of the main researchers in singular cardinal combinatorics and has successfully applied many set theoretic methods to other fields like algebra or analysis, and I believe we'll see a few examples of that today.
Right, well, I'd like to start by thanking the organizers of this program for inviting me. I'm sorry that Peter Koellner can't be here, but I believe that he's going to watch the video of this. I'm looking forward to discussing these ideas with him. So I should start by saying a couple of things. So I'm not, by training, a philosopher. I'm a mathematician, and so there's going to be a lot of mathematics in this talk. Hopefully that's not a problem. It's actually a feature, in my view, as I'll discuss at the start of the talk. Let me see, that's probably the main thing I want to say. The other thing I want to say is, to some extent, I've set out to provoke, and I've kind of wandered in the talk through mathematics, the history of mathematics and philosophy, so there should be something in the talk to irritate almost everyone with any luck. So let me start by kind of stating a thesis. There's going to be various theses which I'm going to propose and try and defend in the course of this talk. And my first thesis is that if you're going to do the philosophy of set theory, or really the philosophy of any area of mathematics, you should stay close to the actual mathematical practices of practicing set theorists. And in particular, you should actually look at some mathematics, and you should look at it in the context of the history of the area that it involves, and also in a kind of sociological way in terms of the communities of mathematicians that are involved. So that's the kind of philosophy of set theory, if you like, that I approve of. And so this talk is going to be an experiment in trying to talk about the philosophy of set theory in this way through a series of case studies of actual theorems in set theory and what you can learn from them about about set theory and about what a possible philosophy of set theory might be. So without further ado, my second thesis, which again, to me, seems uncontroversial, but it seems that not everyone believes it, is set theory is a branch of mathematics. It's not some special thing. It's not, more than any other part of mathematics, if you like, foundational. I mean, it happens to be a part of mathematics in which issues of logic in various ways are very prominent. It happens to be a part of mathematics in which issues of independence are very close to the surface, and in which ideas from logic have proven very powerful. And in fact, we'll see ideas from logic used to mathematical ends throughout the talk. But I assert that it is mathematics, and it should be judged by the same kind of standards that you would judge any other piece of mathematics, which, depending on your tastes, might be elegance, applicability, generality, so forth. So in particular, like any other field of mathematics that's doing well, progress in set theory is kind of a complex process in which, at any given historical moment, there's an internal development in which the ideas of the subject are being elaborated, and a kind of external development in which you're interacting with other areas of mathematics. And again, obviously it's limited time and limited knowledge. I've tried in the course of the examples that I'll give in this talk to kind of illustrate this kind of interplay between internal developments and external developments. So I have more theses. Here's another thesis. I should say that this talk is to some extent a reworking of a talk that I gave at the workshop on set theory that was held at the University of Pennsylvania in Philadelphia in 2010. And in particular, thesis 3 was kind of the main thesis of the talk that I gave there, of which the first part of this talk is kind of a detailed reworking of material from that talk. So my argument here is that one of the distinctive things, as we'll see, about arguments in set theory, there's a very free play of ideas involving a wide range of methods and a wide range of objects. And if you look at the subject historically, you can see that there's been a series of transformations. I mean, the introduction of new methods, the introduction of new objects, old objects viewed in new ways. And again, I mean, this is normal in any field of mathematics that's kind of making progress. But in particular, I want to sort of lay down a marker and say we should be very suspicious of arguments, especially extra mathematical arguments, that tend to put any limit on what the objects or methods are that we can use. That stealing an idea from Paul Feyerabend's work in Against Method on the philosophy of physics, I'm inclined to say that you should compare. So if someone takes a stance which puts some restriction on methodology, then you can kind of look at it critically by comparing it with a very liberal stance or an anarchistic stance which just says anything goes. And then if it doesn't beat anything goes, then it's not a good stance. So I'll say something about that a bit later in the talk. So in particular, there's been a lot of emphasis on the continuum hypothesis, CH, in this series. In particular, a lot of emphasis on proposals for settling CH, also some argument about to what extent CH is intrinsically vague and so forth. So I want to take a kind of slightly different tack here. I want to say, again, if you look at things historically, obviously questions about the meaning of CH and the truth value of CH have been mathematically very fertile. I mean, leading, for example, to basic things in the subject, like the invention of the constructible universe or the discovery of forcing. But again, typically in mathematics, as mathematics develops, I mean, as the mathematics of set theory has developed, so questions around CH have given rise to a new area in set theory, sometimes called set theory of the continuum, though I'm not sure that's a terribly good name. And set theory of the continuum, as these things will, has taken on a life of its own. And if I get that far, my second example in this talk will be a kind of success story involving very heavily the set theory of the continuum, in which somehow, the original continuum problem just isn't somehow the main point. In fact, if you look at set theory of the continuum as a mathematical area in its own right, it would actually be a kind of a body blow to set theory of the continuum if the continuum problem was settled in the positive direction that CH is true, because the biggest part of set theory of the continuum is a rich theory or set of theories in which CH is actually false. So anyway, in digest, I'm going to say, this is the fourth thesis that I'll present and defend. There's actually more to the continuum than the continuum problem. In fact, from some points of view and from some purposes, the continuum problem might really just be somewhat beside the point. And my last thesis, and this kind of builds on the previous one to some extent, is the question of independence and how big independence in set theory should loom in our thoughts. So earlier in this series, we've heard from Hewitt and some very ambitious proposals for doing away with many of the instances of independence in set theory. And maybe that will pan out and maybe it won't. But I think what I'm trying to say here is that it's possible to overstate the extent to which the independence phenomenon is a problem. It's possible to live with the independence phenomenon. It's possible to do good mathematics in an area where the independence phenomenon is just rife. So again, and I'm skeptical that I will be able to do this example in much detail, but if I have time, I want to work through a result by Magador and Scheller indicating what you can do, how you can actually make mathematical progress in an area of combinatorial set theory where independence is just everywhere. All right, so that's the introduction. Those are the theses that I'll be trying to defend, or to be a bit more precise. I guess I'm going to try and give some defense of theses 2 through 5. Thesis 1, that you should do the philosophy of set theory by a kind of detailed study of actual work in set theory, I guess that's the basis of the whole talk. And the success or failure of the talk tells you something about whether thesis one is any good. All right, so let's actually state a theorem. So this is the material, this is the start, this section, the theorem of Scheller. This is the material that I discussed in somewhat less detail in my talk in Philadelphia in 2010. So very classical notion is the notion of a cardinal fixed point, that is a cardinal kappa, such that kappa is equal to Aleph kappa. And something that you probably learned at some point early in your encounter with set theory is that there are many cardinal fixed points, that the function which takes kappa and returns Aleph kappa is continuous. So actually, there are many cardinal fixed points. And the first one is quite low down. It's just the soup of this sequence of cardinals. So it's quite small compared with, say, the first inaccessible cardinal, assuming you believe in that. All right. So here is a theorem about cardinal arithmetic proved by Scheller in the early 1980s and published in 1986. And it tells you something about these very classical objects, cardinal fixed points, and a very classical problem, the problem of how does cardinal exponentiation behave. So it says that you might take issue with Aleph 1 versus omega 1, but that's actually the way he wrote it. So if Aleph delta is the omega 1th cardinal fixed point, then Aleph delta to the Aleph 1 is less than the 2 to the 2 to the Aleph 1 plus cardinal fixed point. So the first point I want to make about this is that it's eminently classical. The statement could have been understood a century ago by the pioneers in the field. Cantor or Hausdorff could certainly have understood it. They might have been dissatisfied with the way that it's stated, but no, I guess it's a fairly absolute-looking statement. I guess you could complain that it doesn't determine the value of Aleph delta to the Aleph 1 exactly, but right. However, I want to discuss in some detail the ingredients that go into the proof, and this is kind of in support of various things that I kind of stated in the introduction. It's in support of the idea that set theory uses a wide variety of methods with a complex and tangled history, and that if in the past you'd taken seriously some view of set theory that was restrictive about which topics you should be interested, which objects you should consider, which methods you should use, then you probably couldn't prove this theorem. So I'm going to talk about each ingredient in turn in a little bit of detail. So there are large cardinals, inner models, the covering lemma, which is something about the relationship between inner models and the universe of set theory. There's forcing under the guise of generic elementary embeddings, and there's also the theory of infinite games. So let's take it from the top. A Ramsey cardinal, it's kind of, from the modern point of view, a fairly low point in the large cardinal hierarchy. So Ramsey cardinal is a cardinal which has a certain partition property. The partition property says that if you two-color the finite subsets of kappa, then there's a set which is as large as you could ask for. There's a set of full cardinality. And it's as homogeneous as you could ask for in the sense that your function is constant on the set of n tuples for every n. You couldn't hope for the function to be constant everywhere because it might take your finite sets to the parity of its cardinality or something stupid like that. So historically, Ramsey cardinals a part of Ramsey theory or partition calculus. So the general philosophy of Ramsey theory is sometimes expressed by saying complete disorder is impossible. In this kind of setting, what we're saying is any coloring of finite tuples from a large set looks very regular on a large subset. So here, it's very large and very regular. Again, to give some idea of the kind of the richness of the ideas that are going into this, you can also look at the property of Ramsiness in a model theoretic light. It says something about sets of indiscernibles in a model of some kind. A set of indiscernibles is a set where you can't, using some formula of some language, distinguish the elements. And hopefully it's plausible that Ramsey cardinals have got something to do with indiscernibility, because you can imagine coloring a tuple using some information about which formulae it satisfies. That's the idea there. All right. So the next ingredient is core models. So there is a kind of terminology problem here. Some people would say inner models, some people would say core models. Some people would use the word core model more restrictively. But so again, another structure that I think everyone encounters early in a study of set theory is the constructible universe L, and everyone learns probably that it's got certain nice structural properties. So, for example, the continuum hypothesis holds in L. The generalized continuum hypothesis holds in L. And something else that's actually fairly easy to see is the smaller kind of large cardinal is actually, as we would say, downwards absolute to L. That if you have an inaccessible cardinal in V, you have an inaccessible cardinal in L. So in L, you can live with small, large cardinals. On the other hand, and again, this goes back a long way, it was observed in the 60s that measurable cardinals, or even Ramsey cardinals, can't exist in L. So if you want to use ideas from the theory of L in comparison with large cardinals, you need bigger models. All right, so another idea we need is the idea of relative constructibility, which I believe is originally due to Heinal. I'm not sure who to credit for that. So the idea is that given a set of ordinals A, in the same way that L is the least model containing all the ordinals, L square brackets A is the least model containing all the ordinals and having A as a member. And as you might possibly hope, the structure of L of A is like the structure of L once you go high enough. If you remember the role of the condensation lemma in the elementary theory of L, then you can probably see why it should be true that if you go high enough above A, then the structure will start to look very L-like. So in particular, above the soup of A, L of A looks a lot like L. Low down, of course, L of A could look very different from L because, well, here's two examples. A could be a predicate coding a measure on a small measurable cardinal, and then L square brackets A will see that small measurable cardinal as measurable. Or A could be some kind of generic predicate. A could be a subset of omega 2 coding omega 2 generic subsets of omega. So certainly GCH could fail low down in L square brackets A. The inner model program is a program which aims to construct, well, okay, this is Whiggish, but aims to construct L-like inner models which can accommodate larger cardinals, cardinals which are ruled out by V equals L. So this is a very cultivated and technical subject, But for the purposes of today's lecture, we don't need to go too far. We just need to go to we need to go to a model called K. Well, to be technical, we need to go to the Dodd-Jensen K, but fortunately that's the only K that we need. So the Dodd-Jensen K is obtained by putting together small models of small transitive set models of set theory, which which see approximations to a measure without actually seeing that there is a measure. So very roughly speaking, what is K? K is the largest L-like model in which there's no measurable cardinal. So this should come with a warning, and the warning it should come with is that L, as again you remember from basic set theory, L is a very absolute concept that any two reasonable models which have got the same ordinals will have the same L. But K is a relative concept. How big K is depends on what's going on in V. But the point about K is it's slightly more hospitable to large cardinals. In particular, Ramsey cardinals can't exist in L, but Ramsey cardinals can exist in K. And in the same way that the construction of L can be relativized to L of A, the construction of K can be relativized to a model K of A. All right. So the next ingredient in this kind of shopping list of ingredients that I need before I can talk about the proof of the theorem is the covering lemma. So the covering lemma starts with something called fine structure, which is a very detailed and careful study of definability and how new sets are constructed as you run the construction of L. So a typical kind of question in fine structure theory might be you take some level L alpha of the hierarchy, which builds L, and you ask, well, we know that L alpha plus 1 is everything first order definable over L alpha. And then we might ask, which is the first ordinal which gets a new subset when you go from L alpha to L alpha plus 1? And then we might ask, syntactically, how complex is the simplest definition of that ordinal? All right, so it's a technical subject, and I think, as Jensen said somewhere in his first paper, it seems like micro set theory, remote from the concerns of the set theorist, but actually micro set theory turns out to have applications in macro set theory. So in particular, I already mentioned K. The theory of K is intrinsically fine structural. But more importantly right now, fine structure theory gives you new internal structural facts that are going to be true in L. Well, I guess diamond isn't completely fine structural, but squares and morasses certainly are. So what these kind of fine structural considerations give you is a very fine internal theory of L, which tells you new things that are true in L. But it also tells you something new about the relationship between L and V. So Jensen's original covering lemma, well, you should think of it as a dichotomy theorem which says that the universe is either rather far from L, in the sense that it can see an elementary embedding from L to L called zero sharp. That's one fork, if you like. The other fork is that L is very close to V in the sense that an uncountable set of ordinals in V can be covered by a set of ordinals in L of the same V cardinality. And in this dichotomy, and I think this isn't very surprising when you look at it, in this dichotomy, if you're in the covering case where L does cover V, then the combinatorics of V in some ways look quite a lot like the combinatorics of L. On the other hand, if O sharp exists, then V really is quite remote from L. For example, if O sharp exists, every uncountable cardinal of V, including cardinals like Aleph omega, is a large cardinal of L. All right, so like anything in mathematics, as soon as it's proved, it's generalized. So for the purposes of the proof I'm discussing, we need a version of Jensen covering which involves a general set of ordinals. And rather than talking about zero sharp, talks about measurable cardinals. And what it says, you've got a set of ordinals A, and you ask a question about A, and you say, again, it's a dichotomy. These two cases are exclusive and very far apart, in the same way that in the covering theorem for L, the two cases are widely separated. So the set A can really live in one of two cases. It can live in a model containing a measurable cardinal, in which case we can't do covering, or it doesn't live in a model thinking there's a measurable cardinal. And in that case, when you build K of A, you get a form of covering, the same Jensen covering, only it only works high. It only works above the suit of A. All right, we're almost there. So again, something that I'm imagining most people in the audience have seen is measurable cardinals. The most fruitful characterization of measurable cardinals is probably to think of them as the critical points of elementary embeddings into inner models of set theory. So this is a point of view due to Dana Scott. The critical point of an elementary embedding is the least point that it moves. If you think about it, the least point that it moves is always going to move up, is obviously going to be regular, is obviously going to be a limit cardinal. All right. So the theory of generic embeddings combines two of our favorite things, elementary embeddings and forcing, and says, let's kind of blur the picture a bit. Let's look at elementary embeddings of V, which maybe don't exist in V, but do exist in some generic extension, Vg. So now we're looking at elementary embeddings which they still have domain V, but they map into some model M. Again, it's a transitive model, but it's a submodel of a generic extension, Vg. And you get all kinds of interesting new phenomena when you start thinking about generic elementary embeddings. For example, the critical point of a kind of ordinary elementary embedding is a measurable cardinal. That was part of the point. But the critical point of a generic elementary embedding can consistently be a small cardinal like omega 1 or omega 2. So this is an interesting phenomenon. And as we'll see maybe at the end of the talk, it gives you the possibility of importing things that you learned in the structural study of large cardinals and using them at small cardinals, that if you can get an elementary embedding which has a small critical point and is added by some reasonable forcing poset, then you can often show that that small cardinal has one of the reflection or compactness properties that are ubiquitous in the theory of large cardinals. And again, that's a topic I'll come back to. So again, life is short, but I just want to say that the existence of generic embeddings can generally be expressed in terms of objects called precipitous ideals. And the property of an ideal being precipitous can be formulated in many ways, but one of them doesn't really even mention forcing or ultrapowers. It mentions a certain kind of infinite game, which brings me to, I think this is the last thing on my shopping list before I can actually say something about the proof of the theorem. So there's and again, this has already come up at least once in this lecture series in Hugh Wooden's talk, probably other places as well. So there's a cultivated theory of infinite games of perfect information. And the way that works is you play on a space which you might think of as infinite sequences from a set X. You've got a payoff set, which is a subset of that set of infinite sequences. And you have two players, player 1 and player 2, who are taking turns, if you like, putting down members of X on the board to build an omega sequence of elements of X. And then when the game is over, player 1 wins if this omega sequence is in the set A, and player 2 wins if the set is outside A. So you might say, well, how do we make sense of this in a kind of more finite way? Well, if you think about it, there's a clear notion of a strategy in this game. A strategy for player 1 is going to be some function defined on sequences of even length, telling player 1 what to do next. The strategy for player 2 is going to be some function defined on sequences of odd length, saying what to do next. You can imagine playing a strategy for player 1 against a strategy for player 2 and seeing what the outcome is. And a winning strategy is a strategy that always wins, not surprisingly. And the game is determined if one player or the other has a winning strategy. All right, so there's good news and bad news about infinite games. So the bad news is that assuming the axiom of choice, it's a fairly straightforward exercise to construct a non-determined game. For example, if you want to construct a non-determined game where X is just 0, 1, for simplicity, then what you want to do is you want to well-order all of the possible strategies for player 1 and all of the possible strategies for player 2. There's only continuum many strategies for player 1. There's only continuum many strategies for player 2. You've got enough elbow room to diagonalize against all strategies for player 1 and all strategies for player 2 and build an undetermined set that, in just the same kind of spirit as the construction by Vitali of a non-Lebesgue measurable set, you've just constructed probably a topologically very nasty set. And in fact, Tony Martin proved that games with Borel payoff sets are always determined for any X. And there's a whole genre of theorems saying that if you assume large cardinals, then you can get determinacy in various contexts for various kinds of payoff sets. So I think I'm not actually even going to state the theorem I need. All right, so that was all a bit long-winded, but can finally get to the point. And when I learned this theorem, I was really surprised that you can actually prove anything this way. So, okay, so for some technical reason, you're interested in the cardinal mu, which happens to be 2 to the 2 to the alpha 1 plus. And you're going to ask the following question. You're going to ask, for every possible subset of mu, you're going to ask a question about that set. You're going to ask, is there a model of ZFC plus there exists a Ramsey cardinal? Actually, yeah, I guess Ramsey cardinal is the natural thing to ask in context. Such that A is a member of M. And now one of two things can happen, but they're both good. Right? So one thing that can happen, you might find an A such that phi of A fails. So that means there's no inner model of A which contains a large cardinal. So in that case, we could actually appeal to the theory. There should be square brackets. K square brackets A, the same object I was talking about before. You can actually appeal to the theory of K square brackets A. You're kind of in the anti-large cardinal case if phi of A fails for any A. If you're in the anti-large cardinal case, you can appeal to the fact that there's a resemblance between V and the inner model K of A, which believes GCH up above the sup of A. And you're in excellent shape. You can prove the theorem. Case 2, well, otherwise. Okay. Otherwise, for every A the statement phi of A holds. So otherwise, every subset of mu lives in a model with a measurable cardinal. I mean, this could happen in any one of various ways. I mean, maybe there really is a measurable cardinal in B way high. Maybe something else happens. But every A of the relevant kind lives in a model with a measurable cardinal. So I said there's this whole genre of determinacy theorems which say, given such and such a large cardinal axiom, such and such a game is determined. And the fact that you've got this large supply of models with measurable cardinals is enough to prove that the good player wins a certain precipitousness game, and victory in the game leads you to a certain generic elementary embedding. And again, the generic elementary embedding leads you to the conclusion in cardinal arithmetic that you're trying to prove. All right, so, okay. And also, I mean, this is part of the point of what I'm saying, is that this theorem uses a lot of different ideas, and tracing the history of those ideas would be to write the history of 20th century set theory, which I'm certainly not going to do. So I'm not going to do that. I'm just going to say a couple of things about the history of the ideas that go into this theorem, just to make a point about how wide the net should be cast. So partition calculus, I believe someone, actually I think this, again, this is probably not quite right. I think that I think it was independently discovered by maybe Veresis in Hungary. But anyway, the first appearance that I know of Ramsey theory was in Ramsey's work. Ramsey was interested in problems in logic involving decidability for finite and countable structures. I think maybe Erdős and friends rediscovered it, but Ramsey theories was greatly elaborated in many settings. I don't want to slight, finite Ramsey theory, which was also extensively developed by Erdős. But today, the interesting stuff for us is Ramsey theory in the context of uncountable cardinals. And then, as the theory of large cardinals developed, Ramsey theory turned out to be a kind of essential feature in the theory of small large cardinals, like weak compact and Ramsey. Again, infinite games, an interesting and complex history that in Poland, in I believe the 1930s, Banach and Mazur were thinking about playing infinite games in connection with things like the perfect set property, that they were giving game theoretic characterizations of properties of sets in topological spaces. They resurfaced, I think in the 1950s. Gale and Stewart were interested in something completely different. They were interested in mathematical economics, I believe, and in the modeling of questions in economics by infinite games. And then, again, they kind of got taken up in the 1960s and became highly essential in descriptive set theory and in a model theory. So fine structure. So Jensen's work on fine structure. Obviously, the kind of main intellectual debt is to the original construction of L. But I just wanted to point out that there are other ingredients that go into the mix that recursion theory, or I guess I should say computability theory now, is also an ingredient that there's an idea in computability theory where you form the so-called jump of a set of reals, and questions that are sigma 1 in your original set become recursive in the jump. And this is actually just the same thing that's going on in fine structure theory. You start off with a level of L alpha. You build a new structure called the master code. Think questions that were sigma 1 about the original structure become sigma 0 about the master code. And another ingredient was the study of weak set theories, because if you're going to do fine structure, then you have to kind of bite the bullet and face the fact that the initial segments of L, even the limit initial segments of L, they're not models of the whole of ZFC by any means. So I think Jensen credits work of Karp, for example, on issues in weak set theories. All right, so one more piece of history, that the characterization of measurability in terms of elementary embeddings goes back to Dana Scott. And Scott proved that the generalized continuum hypothesis doesn't fail for the first time at a measurable cardinal using the elementary embedding characterization of measurable cardinals. And that's also part of the DNA of the theorem by Scholar that we're discussing. Though actually, again, there's an intermediate step, which is a proof by Silver that GCH doesn't fail for the first time at a certain kind of singular cardinal. So Scheller's argument is like the grandchild of Scott's arguments. Okay, one more thing. Generic elementary embeddings and precipitized ideals. Solovey was interested in saturated ideals, and which, again, is a kind of fairly classical topic that Ulam, for example, was interested in questions about the saturation of ideals. But Solovey realized shortly after the invention of forcing that you could force with a poset derived from a saturated ideal and build a very interesting kind of generic embedding. And then Yak and Prickery introduced weakening saturation to precipitousness and defining precipitousness in terms of gains. All right, so that was a lot of mathematics. Now I just want to say something about how I can try and kind of enlist it in defense of my theses from the start of the lecture. So I remind you, thesis 2 is that set theory is a branch of mathematics. In defense of that, I just want to say that just look at what's going on in Scheller's theorem. It's just the same kind of thing that's going on in any other kind of ambitious piece of mathematics that I'd make a parallel. It's just the same kind of thing that's going on when someone does, a hard argument in modern number theory that Scheller's combining ideas from partition calculus, from infinite games, the theory of elementary embeddings, to prove a result which doesn't actually mention in its statement any of those concepts. In just the same way that you might prove a innocuous-looking Diophantine statement in number theory, but to get to it, you might have to take a detour through complex analysis, through algebraic geometry, through the representation theory of groups. So I claim it's just mathematics. That's what I'm saying here. It's not any special thing. So my other thesis that I think Scheller's result here has some relevance to is I'm claiming you shouldn't adopt a view of set theory that is going to place undue restrictions on the objects or methods that you consider. And I think Scheller's theorem is a case in point that if you were adopting a philosophical view or a mathematical view that would discourage you being interested in large cardinals, or fine structure, or the theory of infinite games, or any of the other topics that came up in the course of the proof, then it would be much harder to prove Scheller's theorem. In fact, I can't imagine how a proof of Scheller's theorem could go that wouldn't go through these kind of deep 20th century developments. So another point, which I think I didn't actually encapsulate in a slide, but I think it's kind of an interesting one, is if you look at the kind of history of set theory in terms of the set theoretic developments that were needed for Scheller's result, you see an infusion of new methods, and you also see an infusion of new objects. So you see, for example, many ideas from logic. So you're no longer just talking about sets. You're talking about higher type and logical objects like models of set theory and elementary embeddings between models of set theory. And later in the argument, you're thinking about forcing constructions. But somehow, I still want to say, you don't want to exaggerate the role of logic here, that Schiller's result isn't an independence result. It's an absolute result of ZFC. It's just that in the course of the proof, techniques from logic and techniques that are also useful to prove results in logic or invented to prove results in logic just turn out to be very useful. Okay, so maybe I did say something about this. So, yeah, so new methods and new objects, new views of existing objects, and exchanges of ideas with mathematics, with other areas of mathematics. So again, here's another analogy that I think is actually quite nice. That if you look at the history of algebraic geometry, that sometime, I guess, in the I don't know exactly when to date it, sometime in the middle of the last century, algebraic geometry went through a conceptual revolution in which the geometry was somehow incorporated into algebra, and new points of view were taken on old objects. So, for example, if you adopt this modern view of algebraic geometry, it's very natural to think of a point as being really the same thing as a maximal ideal in some kind of ring of functions. And that leads you to think, well, maybe the prime ideals in that ring of functions should also be considered as some kind of point. So it's a little bit of a stretch, but in the same kind of way, we're not just introducing new objects, we're taking new points of view on old objects. So for example, at a certain point in the Schiller argument, it's critical that you take a set of ordinals A and you start thinking about it in a new way. You think of it, it's a potential member of a transitive model of set theory with certain structural properties. So the set's just the same set that it was before, but now you're looking at it under this new guise. You're saying it's a potential member of a model of set theory, and we can ask, what kind of structural properties do the models of set theory to which it belongs have? And considerations of that kind are exactly at the heart of that dichotomy that finishes the proof. All right, so that's actually all I wanted to say for now about that. So I want to move on, and I want to say something about CH and the role of CH in set theory. So again, I want to discuss a result which actually has a very different flavor from the first one. So this is a result of Ilias Farah that appeared fairly recently in the Annals of Mathematics. So in a paper called All Automorphisms of the Calkin Algebra Are Inner. And the theorem says that if a certain axiom holds, Ta holds, then all automorphisms of an object called the Calkin algebra, which I'll kind of discuss in a very casual way, are inner, whatever that turns out to mean. And after I've given the mathematical background, I want to discuss the set theoretic ideas that go into this proof. And then I want to use it as an example to kind of support my thesis that actually there's more to the continuum, there's more to the set theory of the continuum than the continuum problem, and that maybe whether the continuum is LF1 or bigger than LF1 isn't the central point here. All right, so okay, a very quick refresher course in functional analysis. So we're going to look at a complex inner product space, a very familiar complex inner product space, the separable infinite dimensional Hilbert space consisting of infinite sequences of complex numbers, the the sum of the squares of their absolute value converges with the usual inner product. All right, so this is obviously a pretty significant object in functional analysis. All right, we're not really interested in H itself. We're going to go up a type. We're interested in B of H, which is the space of continuous linear maps from H to H. B stands for bounded. It's an easy fact that a map is continuous if and only if it's bounded, in the sense that it doesn't stretch vectors by more than a certain amount. And you define the norm of an operator by asking how much it stretches vectors in the unit ball. All right, so B of H, it kind of starts life, well, it's a collection of linear maps from a complex vector space to itself. So B of H is a complex vector space. But if you put this norm on it, then it becomes a complete normed space. That's to say, it's a Banach space. It's closed under composition. The composition of bounded operators is bounded. Composition's bilinear. So by putting on more structure, B of H becomes a kind of structure called a Banach algebra, which I think I won't list the axioms. But there's more structure yet. There's this star operation, the adjoint, I guess, so that if you have a linear operator T, there's a unique T star satisfying that equation. Everyone's seen this in matrix algebra too, that if you're in a finite space, this is just the, what's it called? Conjugate matrix, the Hermitian conjugate matrix. All right, so we can look at this stuff abstractly, and we can say, what kind of structure have we imposed on B of H? And the kind of structure we've imposed on B of H, it's a Banach algebra with an involution, that's what it's usually called in this context. And the involution map satisfies a list of identities. So abstractly, a C-star algebra is a Banach algebra equipped with a map A to A star satisfying the same finite list of identities that are satisfied by the adjoint map T goes to T star. All right. So, well, why should you care about C-star algebras? Well, there's a kind of completeness theorem called the Gelfand-Naimark-Segal theorem, which says that C-star algebras are exactly the algebras which will show up as norm-closed, star-closed subalgebras of bounded operators on some Hilbert space. And the unital commutative C-star algebras are very, very nice objects. They're exactly the things that show up as spaces of complex valued functions on compact Hausdorff spaces. So a kind of slogan that you can adopt is you can think of the theory of C-star algebras as a kind of non-commutative geometry, that it's doing the same kind of things. I mean, somehow there's no topological space in quite the same sense there anymore, but it's profitable sometimes to think of C-star algebras as consisting of functions on something. All right. So one more bit of analysis. A compact operator is one such that the image of the unit ball under the operator has a compact closure. So you should think of these as being close to finite dimensional in some sense. They're limits in the appropriate sense of operators whose range is finite dimensional. So again, this is a very natural class of operators to study in the context of things like, say, the spectral theorem. And it forms a C-star algebra, not with a unit. It forms a C-star algebra, which is a C-star algebra ideal in my original algebra B of H. And so you can form a quotient object called the Calkin algebra. And you can think of the compact operators as finitary, and you can think of the Calkin algebra as consisting of blurring your vision and looking at operators just modulo finite perturbation. So one more thing. Just like in elementary matrix algebra, we've got this notion of a unitary element in a C-star algebra. That makes sense in any C-star algebra with 1. And if you have a unitary element, it's the same definition, U and U star are inverse. If U is a unitary element, then you can conjugate by U and get a C-star algebra automorphism of your C-star algebra. And automorphisms of that type are called the inner automorphisms. And a classical question that was posed by, I think, Brown, Douglas, and Fillmore asked whether it was true that all automorphisms of the Calkin algebra are inner. All right, so progress was made by Phillips and Weaver, who showed that under CH there is an outer automorphism. That's one that's not inner. So that construction is actually, I'm given to understand by Ilias Farah, the construction is pretty hard. You know, we tend to think of, if you prove something using CH in kind of combinatorial set theory, well, you just enumerate maybe the countable subsets of omega 1 in type omega 1, and you get diagonalizing. And in set theory, that's fine. But in C-star algebras, apparently you have major problems at the limit stages of this kind of construction, diagonalizing against the possibility that your automorphism might become inner. All right. So Farah closed this problem by showing that assuming an axiom TA, which I'll gossip about at least in a bit, all automorphisms of the Calkin algebra are inner. So again, and this is something we kind of see all the time in the progress of mathematics. Analogical reasoning will get you a long way as long as you use the right analogies. So Farah's work, there's an underlying insight, which is a series of analogies between this kind of functional analysis machinery and some set theoretic machinery that's probably a little more familiar to us. The theory of the Boolean algebra P omega and the quotient algebra P omega mod finite. So in this analogy, you've got P omega as a Boolean algebra versus the Banach algebra BH. I guess the C-star algebra BH, I should really say. The ideal of finite sets is going to be analogous to the ideal of compact operators. And the quotient algebra, P omega mod fin, is going to be analogous to the Calkin algebra operators, modulo compact operators. And you can push the analogy further. For example, you know, the singletons in P omega would correspond to projection maps onto one-dimensional subspaces in the algebra K of H. All right, so here's an easy thing. Take an automorphism. When I say automorphism, I'm thinking of P omega as a Boolean algebra. I mean a Boolean algebra automorphism. So what I'm going to say is an automorphism of P omega is trivial if it's induced by a permutation of omega in the obvious way. And it's not hard to see. P omega doesn't have a very interesting structure. P omega is an atomic Boolean algebra. An automorphism of P omega is going to permute the atoms and be determined by the way that it permutes the atoms. So obviously, all automorphisms are trivial. But if we quotient out, so remember, when we form P omega mod finite, we're identifying two finite sets if one of them's a perturbation of the other. Then this nice argument goes away. So again, for technical reasons, I shouldn't be thinking about permutations. I should be thinking about bijections between cofinite sets. But that turns out to be the right thing. So we're going to say that an automorphism of P omega mod fin is trivial if it's induced in the same way by a bijection between cofinite subsets of omega. And now we can ask, are all automorphisms trivial? It's an old question. So Walter, this is Walter Rudin, not Mary Ellen. Walter Rudin showed that if you assume the continuum hypothesis, then there is a non-trivial automorphism of P omega mod fin. And that argument's actually pretty easy and kind of familiar to a lot of people in this room. It says P omega mod fin under CH, it's going to be a saturated Boolean algebra of cardinality LF1. Therefore, it's going to be rich in automorphisms. It's going to have 2 to the LF1 automorphisms. But hey, there are only 2 to the omega permutations, and we're assuming CH. So by that rather non-constructive argument, there are so many automorphisms of P omega mod phin that one of them isn't trivial. And then one of the standout theorems in Scheller's proper forcing book is a consistency argument showing that it is consistent that all automorphisms of P omega mod phin are trivial. But that's a tough result. That requires the invention of a new iterated forcing technique called Oracle CC. And you end up with an argument which is rather specific to P omega mod phin. And that's a pity. If you like this kind of chapter of set theory, there are lots of other natural ideals on omega. You might be interested in P omega modulo ideals other than the finite ideal. And then you're out of luck. The argument doesn't tell you anything. So Scheller and Stefrans took a very different tack and showed that, and the argument, it really is different from the forcing argument given above, that a sufficiently strong forcing axiom called the proper forcing axiom actually implies that all the automorphisms are trivial. And this is a better argument from many points of view. So, but continuing the history, Berman Velichkovich, and I've left out some of his diacritical marks, Berman Velichkovich showed that actually, if you take the conjunction of MA and an axiom called TA, that already implies that every automorphism of P omega mod phin is trivial. And the advantage of this approach is that now it's much more generalizable. Earlier work by Ilias Farah showed that you could run similar arguments in the context of quotients of P omega by other ideals. And it was this line of investigation which led to Farah's solution of the C-star algebra problem. I should just say, what is TA? TA is a Ramsey theoretic axiom. It's sometimes known as the open coloring axiom, but one shouldn't probably call it that because there's a clash of terminology potentially. So better to call it Todorciewicz's axiom. It's an axiom which says if you take a certain kind of partition in, with some topological properties in some topological space, then you get a dichotomy. Either you get a large homogeneous set in one color, or the whole space is a countable union of homogeneous sets in the other color. So I'll spare you the details, but it turns out that this is the argument that you can use, or ideas from this argument are the ideas that you can use in the setting of the Calkin algebra to show that under this axiom, all automorphisms of the Calkin algebra are inner. All right, so what to say about this? So this would be my kind of case in point. So here's a piece of mathematics which, in some sense, it's clearly in the orbit of CH, but really it would be misleading to think of it as really having very much to do with the continuum problem. And also I want to make a point about the role of logic. I mean, formally, you can certainly think of it as an independence result. If you combine it with the Phillips and Weaver result, it tells you that there's a certain question about the Calkin algebra which is independent of ZFC. But somehow, that's doing it an injustice. You shouldn't really think of it as just that ho-hum, just another independence result. It wasn't proved by those kind of, I like coding as much as the next person, but somehow proofs where you just code in some clever way objects from one field and another field, somehow they don't tend to to tell you the things you want to know. So it wasn't proved by some clever coding, and it wasn't proved by some elaborate forcing construction. So it's actually proved by infusing ideas from set theory of the continuum into the study of the Kuhlkin algebra. And it's been mathematically fertile in a way that those kind of forcing arguments and coding arguments often aren't. So for example, it gives you new ways of thinking about automorphisms of the Kuhlkin algebra. For example, I said the Phillips-Weaver theorem is tough and uses a lot of deep C-star algebra theory. But Farah's work gives you a new way of doing the Phillips-Weaver theorem. And as a kind of sociological point, it's important because it kind of opens up a bridge between two areas which have kind of actually historical roots, I guess, in the work of von Neumann, but have been quite widely separated. And you open up a bridge which joins 2 points of interest, and traffic starts flowing in both directions. So it's not just, this is true, it's not just that people are using new set theoretic methods in C-star algebras, but there are new problems in pure set theory which come from this bridge. So for example, several people are interested in this kind of thing. There's a whole area of set theory where you study objects called cardinal invariants of the continuum, which are various cardinal numbers that you can associate with P omega mod phi. So it's a very nice source of problems in set theory to start thinking about the cardinal invariants of the Kuhlkin algebra. But just one more thing. So another vexed question is new axioms. Does mathematics need new axioms? What kind of new axioms does mathematics need? So here's a case in point of, so here's a strong, and maybe by some people's lights, implausible axiom, the proper forcing axiom. So the proper forcing axiom, it's only known how to prove it assuming the consistency of a supercompact cardinal. It can only be proved, as far as I know, by some kind of more or less complicated, iterated countable support proper forcing construction. So it's kind of, it's a high-tech item, but it appeared in the history of the development of the ideas that led up to the proof of Farah's theorem, even though it then disappeared again. But it was important. Somehow, it was an obvious candidate for an axiom that would be strong enough to prove that there are no automorphisms. Somehow it's too strong for the job, but once you know that it does the job, you can distill the axiom that actually does the job. And so, again, I want to kind of just give that as a kind of possible other perspective on the search for new axioms. I just think the search for new axioms is something that set theorists naturally do. It's somehow part of how we work on set theory is by looking for new axioms. And we're not necessarily motivated by the independence phenomenon very directly. We're not motivated by saying, here's this great new axiom which you should actually believe, which is going to resolve famous open problems. A new axiom can just be a tool. Let's see. So I think I'm going to run into awful time trouble, but I do want to. I guess it's a shorter section. All right. So I'm going to attempt to go through the last section. At a certain point, I might have to start hitting the button quite fast. All right. So my last thesis, I think it was thesis 5. My last thesis is that maybe independence is overrated. Maybe we shouldn't regard independence as such a problem. Maybe we can still make progress in a situation where there's a lot of trouble with independence. So my last case study is going to say something about this. it's going to be an example of a series of results, really, proved in an area where there's a lot of trouble caused by the independence phenomenon. You have to work around it. All right. So it comes from a paper, which I didn't give you an exact reference for. It comes from a paper called When Does Almost Free Imply Free by Magador and Schaller. As the name of the paper suggests, it comes from a problem about free groups. But I'm going to suppress the kind of general setting, which is actually even more general than group theory. I'm going to just discuss a kind of special case of the circle ideas involving transversals of families of sets, which is, again, a well-studied thing in combinatorics. So a transversal is just a 1-1 choice function. It's just a function that selects from a bunch of non-empty sets an element of each set in such a way that different sets get associated with different representative elements. And it's easy to see from the compactness theorem that if you've got a family of finite sets and every finite subset has a transversal, then the whole thing has a transversal. But things get more complicated when you start thinking even about families of countable sets. So I haven't done too many proofs in this lecture. Let's do a proof. Take a stationary subset of omega 1 and just associate with each element of that stationary set a cofinal subset. All right. Because they're cofinal, a little bit of ingenuity will let you argue that any countable set has a transversal. Just take your countable set, arrange it in order type omega, and then use the fact that your sets are almost disjoint to choose the transversal. It's easy. But Fodor's theorem, look, Fodor's theorem tells you if you have any choice function, it's really a regressive function on S. Therefore, it's constant on a stationary set. Therefore, things are hopeless. You can't even find a choice function on a stationary set. So let's abbreviate. Given a regular cardinal kappa, let's let R kappa be the assertion. You've got a family of kappa many countable sets. The whole family doesn't have a transversal, but every small subset, by which I mean every subset of size less than kappa, does have a transversal. So this is related to questions, it's not the same thing as it's related to questions about groups that might be almost free, but not almost free in the sense that all small subgroups are free but not free. All right, so we've proved R LF1. So R kappa belongs to it's recognizably an element of a class of statements that comes up a lot in combinatorial set theory. It's an assertion of a kind of incompactness. It says, here's a family of sets with a property, in this case not having a transversal, which isn't shared by any small subset. And here's a good rule of thumb. Incompactness properties, they tend to be true if V equals L, and the negations, if they're consistent at all, tend to be statements which have large cardinal strength and are witnessed by the kind of generic elementary embeddings I was discussing earlier. All right, so here's another kind of reflection type statement. So a stationary set reflects if it's got a stationary initial segment, and the assertion there is a stationary set which doesn't reflect is a kind of incompactness statement. So if you have a non-reflecting stationary set, it's stationary. No proper initial segment is stationary, so it's got a property not shared by any of its initial segments. It's easy to see that if you look in LFN plus 1, if you look at the points of cofinality LFN, that's actually a non-reflecting stationary set. It's a nice little set theory homework exercise. And a very general theorem of Milner and Schaller says that non-reflecting stationary sets have a powerful stepping up property. Again, this is something that's quite ubiquitous in this kind of set theory, that you have to proceed very often inductively, and that puts a premium on results that lets you take combinatorial assertions and push them up from a smaller cardinal to a larger one. So if you have a non-reflecting stationary set in lambda consisting of kappa points, you can push up a kappa example to a lambda example. So R kappa is going to imply R lambda. And we've got all these non-reflecting stationary sets from the previous slide, so we can inductively prove R LFN for every n. And we would like to prove or disprove R LF omega plus 1. Well, first stab, you might say, let's just take a non-reflecting stationary set in LF omega plus 1. If you have one, which under some circumstances you do, if the world is sufficiently L-like, you actually have such a thing. But Magador gave a consistency argument that actually every stationary subset of LF omega plus 1 can reflect. So you seem to be stuck. I'm going to suppress that remark. All right, so you might begin to speculate, because of Magador's theorem, you might speculate that R LF omega plus 1 is an independent statement. But that'd be premature, because Shah has this thing, this PCF theory, which is a powerful theory built in ZFC about the combinatorics of singular cardinals. And PCF theory lets you isolate another stationary set, which is called the good set. And you can use the good set in place of the non-reflecting set to do a stepping up argument to show that actually R LF omega plus 1 is true. And again, there's a kind of general phenomenon here that ZFC is a surprisingly powerful theory. One respect in which it's a surprisingly powerful theory is it has L-like consequences. So really the idea of the previous slide, there's an L-like consequence, the stationarity of the good set, which is enough to prove the theorem. All right, so now we've got to LF omega plus 1, and we can start using induction again, and we can get R kappa for all regular kappa less than omega squared. And now we want to push forward to LF omega squared plus 1. So, and here we say, well, let's try and use PCF theory again. And now we don't get complete success, we get qualified success. PCF theory gets you through unless a particularly nasty set, the chaotic set, is stationary. So if the chaotic set is non-stationary, then continue. But maybe the chaotic set is stationary a priori. So that's one of the clues. I mean, it's not the only clue, but that fact, seeing that this, unless you're in this very pathological PCF situation, you would be able to prove R LF omega squared plus 1. That's somehow the key observation in doing a consistency argument to show that R LF omega squared plus 1 is false. And in keeping with this kind of general pattern that I've been talking about, the argument goes through guessing the right kind of generic elementary embeddings. So I guess my thesis 5 is, we can live with independence. We may actually have to live with independence. And my example here is to indicate, here are some ways that you can actually make mathematical progress in a setting which is just fraught with independence. So you can identify some heuristics that were used there, and they've got a pretty good track record in combinatorial set theory. So the kind of heuristics I have in mind are, think in terms of compactness versus incompactness. That's a basic tension in set theory. Think about what's true on the basis of V equals L or its structural consequences. Look around for refined arguments which are similar, but only use L-like facts which are true in ZFC. And then when you get stuck, then you can actually learn something from these failed combinatorial arguments about how the consistency argument should go. And then maybe you can actually do some forcing. And you've got a shrewd idea that your consistency result's going to involve generic elementary embeddings. So it worked here in this problem about free subsets. It works pretty well in a number of problems in combinatorial set theory, thinking about like the tree property, problems about chromatic numbers of graphs, and so on and so forth. So, actually, wait. So I think I promised some challenges. Maybe I haven't actually produced any challenges. So let me actually try and justify my title by saying something about what I think are challenges for would-be philosophers of set theory, that I think you have to say something which is faithful to actual set theoretic practice. And as I said, doesn't impose any undue methodological restrictions, and really is kind of alert to the fact that it's a subject with a complex history, and it's a subject in which new ideas and new objects are being infused, and in which the old objects are being viewed in new ways, and which also doesn't overplay the role of logic and the issue of independence, because there's a lot more to set theory than logic, and there's a lot more to logic in set theory than independence. Okay, so I think I've overrun by 1 minute, so I shall stop.
You remarked that when you were talking about the search for new axioms, you said that these axioms don't have to be true; they can just be tools.
Be useful, yeah.
So,
yeah.
what useful for what, or tools for what?
Useful for example, getting a new kind of conceptual organization on your material, or for getting the right proof, right? That somehow the right proof that there can be only trivial automorphisms in a P omega-mod isn't this awful forcing construction of Shell-R's that was the original proof. It's the much slicker proof that follows from this powerful new axiom, the forcing axiom. So once you've got that proof, then you can then maybe you can throw away the new axiom. The new axiom was just a kind of organizational tool. So, but it's successful in that sense. That's,
I'll have a second.
please. Yeah.
Do you think philosophers of other branches of math in general, should also take into account the history of various parts of their math?
Yeah, no, I mean, it's hard for me to see, as I said, it's hard for me to see how you could do a reasonable philosophy of set theory without taking into account the rise of, the idea that you don't just have sets, you have models, you don't just have models, you have elementary embeddings between models and so forth. And yeah, in the same way, I can't see how you could do the philosophy of geometry without taking account of all the transformations that the ideas of things like space and point have been through historically. Somewhere.